I get you. You wait though. I know. You just wait. Please. Wait. I know. You're such a good boy. You're so good. He really is. Very good boy. Hold on. You wait. Just wait. What? Y'all eat so much turkey. You guys eat like $20 worth of turkey every 3 days. It's ridiculous. My family and their turkey. Wait a second. Wait a second. I hear you. I hear you. That's right. I got you a treat. Oh, listen. Okay, make sure I get all this up. Jack is on vacation. Wait, where does anybody know where's Liam? Don't know? Not keeping tabs on him? Caitlin? Is he? Okay. No. Okay, we don't need to. Just wondering if anybody knew where he was and make sure he's okay. He's not like something terrible didn't happen or whatever that we missed. Oswald, I see you. You need to wait. I have it right here. I'll give you treats. Wait a second. I'm gonna make sure everybody is situated first, okay? That's a right would. Okay.
Something getting electrocuted from the sky.
Yeah. No. All right, Ozzy, place. Wait there. Good boy. All right, so we got everybody. We're situated. Just missing my offspring. I don't know where he went. All right, so we are doing meteorology today. So the other guy's stuff doesn't exactly line up with yours. We're going with yours first. So theirs was a little repetitive today, whereas yours is new. So we're gonna do some weather stuff, which makes sense because you guys are going to be doing all the weather reporting and it's going to be fun, fun, fun. And look, I got smart. I found a new way to do your money. I found an ice box with little ice trays that are in like shelves. So I don't have to put out the mat and worry about things falling over. All right, so let me hand out stuff I owe you first. Where'd Piper go? Piper, you have a lot of stuff here. This is yours and you had 2 Ricos.
Yeah. Today's is very interesting. I've been quoting green screen.
All right. Drew, you have this, Bailey.
I want a suit.
That's Bailey. Alex, that's you.
Yes, I know.
Also, I can't kick someone in the face, he's a suit on.
I was supposed to wear this.
Yeah. T-shirt.
There you are. Oh, another one for you. And
Also.
yeah. Now we got everybody situated. Here, good to go. Jack, and he's not here. I'm gonna grab a cheat. You just there. See you. All our cheese sticks. All right. Yeah. He was there at school. Where did you go? He was.
Awesome hush.
I think I must do. Like There was the voice line, there was.
Lost Mitchell, they're gonna see.
Atlanta.
Mother will find him. I think Cole has the staying out in the driveway, so, place,
Yes.
yeah. So I think Mitchell's over there checking out. Place, hey,
Coins.
there you are. Your mother found you. Where'd you go?
Doesn't matter.
You were in the bathroom. So when I said Mitchell, you didn't answer.
Yes.
All right, that makes sense. Okay, weather, causes of weather. So what word am I looking for here? Study of atmospheric phenomena. All right, Ms. Piper, what am I looking for? Okay, if you didn't know what that meant, how could you figure it out? By the word itself, Bailey?
Good word. Meteorology.
Yeah,
Never mind, I thought I had written it down.
that's okay. What about Alex?
It's etymology.
Etymology.
Means the air, and ology is study of or
There
study,
you go. So what's biology?
study of life.
There you go.
Study of life. What's astrology?
Study of the stars in space.
There we go. All right.
No.
It's a little different. It's more like,
Is much more of a pseudoscience.
yeah, it is. That's a good way to put it. But they do study constellations and mhm.
It's a goofy awesome.
It's a goofy what?
Goofy awesome.
Awe science? Okay. So yes, meteorology is what we're looking for. Remember, ology is the study of. So any root you put in front of it describes what you're dealing with. All right, so we have three main categories of what we call meteors. Okay. One of them is precipitation, and it has a word for it that has meteor in it. Then we have one that's dust, smoke, haze. And then we have one that's thunder and lightning. Does anybody know what kind of meteor precipitation is?
Water.
Water. You're very close.
Why?
Think about that. You just said water. Think about it.
Hydro something.
There you go.
Meteor.
Hydrometeor. Good job, Drew. You want to take those words that you know? All right. This one says smoke, dust, and haze. Where did the smoke and the dust come from? Yeah. Where they come? Bailey, Chloe, somebody. Go ahead, Chloe.
Particle, like, it comes from the space that
Mm.
forms it.
Yeah, or from the ground if it gets picked up and thrown up there. So what do we think is the word we're looking for here? Does anybody know? Alex, do you know?
Is it geometeor?
Not, but that's a good guess. Okay, it's lithometeor. What's litho?
Stone.
Hey, very
I
good.
remember stone.
Mm-hmm, mm-hmm. This last one's tricky. This one is electrometeors, which makes sense, thunder, lightning, right? Cool. This is a great exercise in Greek and Latin and scientific roots and whatnot. Really good one. All right, so these were just cool pictures. I really particularly like this one at the bottom and this one here. That's just cool.
That one on the right looks like a giant thunder snake is coming out.
Yeah.
It's gonna just
For real.
destroy your entire life.
See, this reminds of some Greek god.
It's massive for sure.
Yeah.
So weather and climate, you guys should know this one. The difference between weather and climate. So atmospheric phenomena interact to affect the environment and life on Earth. So what do we call the current state of the atmosphere, Milo?
Weather.
That is weather. And what is the average over 30 years, James? That is climate. Great. Okay. So remember those two. You guys had that. That's pretty easy. You know what you're talking about because you've done it many times. All right. So it's about balance here. Weather's about balance. Obviously, you want some warm, you want some cool, you want some water, but you don't want to be flooded, right? So you have to get some balance.
Fish.
Right. And Earth is imbalanced in the way it is heated. And why is that? Drew.
I have a question. Are you referring to, like, I'll make it up. Axis, because obviously,
Look at the picture. Does that help you?
oh, that, well, it's for the way the lights to travel a longer distance.
Uh-huh. So what did we call that? It's got something to do with Earth's. Bailey, you know? Yeah. What about its axis? Atta girl, it's tilted on its axis, right? So Earth's tilted, and because of that, the sun's going to heat the surface of the Earth unevenly. That's how you get what? Was it? Yeah.
That's one reason why the equator is so much warmer.
Mhm.
Also so much colder.
Yeah, and why is our weather getting cooler overall right now? Like what's going on?
Winter is coming.
Yeah, Bailey? Right, because of the way it's tilted, we have seasons, right? Seasons arise because of the way we have our earth tilted. So here's a question. Why don't temperatures continue to increase at the equator and make it even warmer than it already is? James? Because there's nighttime. It's a good one.
It's constantly spinning.
Earth is spinning, right? But the equator is always roughly the same distance from the sun. That's why they have like less of seasons there than other places do. Like think about Alaska, they have dark days and weeks.
Because of like rain and clouds.
Rain and clouds. That's a good one. What do you think, Alex?
Radiation gets bounced back out.
That's a big part of it. Radiation gets bounced back out, and we'll do one more. Drew?
Oh, I was just gonna point out that, I watched a video and, it said that one of the things you could do to survive longer in space is to do constant flips so that
Oh.
the sun will heat your body.
Ah, okay.
I mean, it's not gonna deal with suffocation.
Yeah, never mind that. Yeah.
If you hold
Well, so what do we call
Explode.
So what do we call the constant movement of air and water? Do we know, Bailey? That's part of it. So this was a little trickier. So this is thermal energy redistribution is what we're looking for. But the point is, the reason why at the equator it doesn't constantly get super hot and just continuously heat up is because air is moving and wind and ocean currents are moving, and they're redistributing that heat all around. If there was no air or wind currents, and we can think of it like this, okay, if let's say you put a big pumpkin on a rotisserie spit and put a fire beneath it, and you turn it, the ends of the pumpkin are not going to get cooked as much as the middle of the pumpkin, right? Because the middle of the pumpkin is going to be closer to the fire because the shape, it's round like that, the fire's down here. So the same thing with Earth, the equator would get super duper hot if it weren't for these currents in the ocean and in air that are going to redistribute that heat so that it doesn't completely fry the equator entirely, because that'd be terrible. That would be bad. So now let's talk about these air masses. What now? Yeah, make an experiment. I don't want to do it. So what do we call a large area of air that takes on the characteristics of the area over which it forms? Bailey, or no, Piper, sorry.
Air mass?
Air mass is what we're looking for. That's right. Okay. So air mass. So yes, characteristics of the air mass can be humidity, dryness, hotness, and it is going to take its characteristics from the region of land that it forms over. And then it can move, which is how you get warm air masses from over the equator away from it and cooler ones to approach it, right? So that it doesn't cook down there. So here are some ways we can classify the air masses. They can be warm and dry, continental tropical, warm and humid, maritime tropical, cold and dry, continental polar, cold and humid, maritime polar, Arctic and Antarctic. What's maritime referring to? James? Yeah, the sea. So if you're near the ocean or the sea, whatever you want to call it, yeah, that's a maritime region. And then other things that we add to the description is where they develop. So this kind of talks both about where they develop and kind of how both of them are, well, they're kind of, they sort of talk about different characteristics, but when you put them together, like you can put the M with something else, doesn't have to be always the same. So like equatorial, obviously those are developing along the equator. Monsoon, these are the ones that are moist and unstable. What's a monsoon? Anybody, Alex?
It's a massive rainstorm, often seasonal, commonly found in places such as India.
Do we get them here in the US?
Not really, no.
We get them in certain places. Do you know where they get them? Here, do you know?
I know
Florida.
Las Vegas has a seasonal weather pattern, but very similar.
Yeah.
But it doesn't have the same extent.
So right in the middle of the country where we have desert like New Mexico, Phoenix, Arizona, those places, they will get monsoons from time to time, which is not great because their ground there, think about the ground, like what kind of soil do they have, do you think, in New Mexico? Somebody just describe it. It's dusty. How else would you describe it? Sand. Are the grains big or small?
Maybe.
Very small. And do you think there's a lot of space between the grains or less space? Less space. Why? Just because why?
They can step.
Yeah, it's been, compacted over the years without, there's not worms, in it tossing it up, and there aren't trees in it with their roots breaking it apart, right? Not everywhere because it's just desert. There could be a cactus here or there, right? But in general, it's not like that. Doesn't have grass. Yeah, so do what?
You can't use desert sand for glass
Why is that?
because of the grain issue. It's
Ah.
big enough.
Grains. Okay, there you go. So yes, so when a monsoon comes, it causes a huge flood. There are dry creeks, like we have dry creeks here that we build to divert water from rain. But there are dry creeks that run in places like this that help divert water. My friend lives in right outside Albuquerque, well, in Albuquerque, at the base of Sandia Mountain, and she has a bridge to go over to get to her house, but there's nothing in it. It's just a ditch. But if a monsoon comes, it'll go there and she can still get in and out of her house.
Along with what you said about desert sand,
Mhm.
you also can't use it to make artificial beaches because it is at different grade size
Mhm.
than beach sand.
Super, super fine. Yes.
Which is why-
No, there's actually a whole underground, beach sand, like
Smuggling rate.
mafia type thing.
Mhm.
It's,
Sand
it's,
mafia.
it's kind of like dust.
Oh,
It's for sand.
for sand. Okay.
It's valuable.
Oz, place. Come here. Come. Hey,
There's like whole mafia
Hey.
bosses for sand.
that's interesting. Mafia bosses for sand. Well, anything that's in demand enough, there will be a black market for it. So now let's talk about source regions. Where do these air masses come from? All right, this is your chance to do some guessing here. So North America is going to typically, never goes lower, typically experience 4 types of air masses, and the climate and weather vary greatly. So typically in North America, we have, I say Arctic here, but it's less common than the others. So we've got tropical maritime, tropical continental, polar maritime, and polar continental. And these are the zones you can see over here with the color. So number 1, anybody want to guess what source region that is? Bailey? Polar maritime. Does anybody have something different, or do we agree? We agree. Okay. So polar maritime, Bailey says, and she's got that right. So maritime polar, they put it here, right there. Same thing. All right. So what is that? I hate it when I do that. Okay. All right. So now I know I squealed. Number 2. Who wants to guess number 2? Alex.
Well, first, you said that there were 4, but there's 5 up there.
Yeah, that's why I said that one is kind of less common. It's a little one. Yeah.
I just wanted to point out, also, I think it's polar continent, Arctic.
Arctic. You think it's Arctic?
Arctic.
Anybody disagree? Agree? Nobody wants to go. So you got that right. It's continental Arctic. So that one's a little, like I said, it's less common because it's in that one little teeny spot, and it's not as big. So how about number 3? Piper, what do you think?
Tropical continental?
Tropical continental?
Wait, no, 3, hold on.
3.
Polar continental.
Polar continental? Anybody agree, disagree?
I concur.
You concur. All right, so let's see. What do we get? Good job. All right, now these were coming obviously down from the pole, so these are going to be coming up from.
The equator.
Yeah. So what do we think number 4 is? Anybody want to guess? Anybody? Bailey, you want to guess? Tropical maritime. Let's see. Look at that. Why'd you guess that?
It's the hot version.
And it's near the water, right? Okay. And the last one. Obviously, that's going to be what?
Tropical.
Yeah, there we go. Tropical continental. So you guys got it. Good job. All right. So I learned everybody is. So yes, these are our typical air masses. Now, when we get these air masses, there's obviously little smaller ones in between that aren't part of this big giant collection. But these are sort of like a general overarching thing. So we can call this air mass modification when they start to move. So they don't stay in one place for very long. And as they move, they're going to transfer heat from one area to another. And they begin to acquire the characteristics of the source region that they travel to. So look back at this real quick. And you've got continental tropical and continental polar. And you see the continental tropical is kind of going this way, and the continental polar is going this way. So you have a little bit of like a kind of a shape here, sort of a big circle. Now, let's think about this. If this air is, so what would continental tropical air be like? What would it be like? Describe it, Alex.
Warm and moist.
Warm and moist. Okay, it's warm and it's wet. And how about the polar continental? What do we think that's like, Drew?
Cold.
Cold and what else? Is it wet or dry?
Wet.
It's actually pretty dry because it's not one of the maritime ones, and tropical is wet just because it's kind of all wet in general, but maritime is going to be way more wet, right? All right, so when they come together, this mass here is going to start taking on the characteristics of this mass here. So think about when, think about what happens when these two masses get together. This is when you're going to get a front. We're going to talk about storm fronts in a minute. So for example, you've got these source regions that are more stable than others. So here is the, what do we say? Here's his polar, wait, okay, here we go. Continental polar. So very cold and dry. And then you've got like, what do? We did the continental tropical. So it's warm and dry, not quite as wet as the maritime ones, but these come together. And when they come together, there are certain things that occur as that energy is transferred. So here's something to remember. This is almost a little inverse, but not. So heat is always going to move from warm to cool, right? The energy doesn't ever go the other way. The energy doesn't ever increase. That would be silly. It would take energy to do that. So it doesn't ever go from cold to warm. It goes from warm to cold. So if two air masses meet and one is warmer than the other, it's going to transfer some of that heat to the cooler one. But because cold air is more dense than warm air, the cold air tends to sink under and push the warm air mass out of the way. So there's this sort of push and pull going on. All right. So let's talk about the systems that evolve from all of this push and pull. So here's a fun one. What is this? The Earth rotates from east to west as it spins. It has an effect on the air. The air is deflected to the right in the northern hemisphere, to the left in the southern hemisphere. And if you look at these guys on this merry-go-round, okay, I don't think these are in parks anymore. Are these, you ever been on one of these? Anybody?
Yeah.
Do you see them in parks?
No.
Okay, so when I was growing up, it wasn't about making this ball curve like that, which is pretty cool. It was about throwing your friends off. Man, we would be dangling, like holding on by a foot, our heads this far from the ground. Us kids that grew up in the 80s were alive by some miracle. Yeah, they're rough. Okay, so Milo, what's this called?
I don't know
Oh.
about one. So we have like little rope diamonds.
Mm-hmm.
That little man.
Mm-hmm. All right, Drew, what is it?
Horse.
No,
Horse.
no. James? It's the Coriolis effect. Okay, now we're gonna do an experiment. I need 2 volunteers. Volunteers. I'll do Chloe and I'll do Piper. Okay, so here's what we're gonna do. You probably wonder why this guy's sitting behind me.
Dun, dun, dun.
Okay, we're gonna hold the Earth with the North Pole facing up. What? Good question?
Also, Coriolis effect has to be accounted for by snipers because
Oh, that's interesting. Yeah, that makes sense. Okay, so when you stand here, when you stand there, so everybody can see. Okay, so here's what we're doing. This is correct, right? If we're looking north being up, this is not correct. So what?
I was gonna just say, fun fact we didn't know, due to centrifugal force in the Earth's rotation,
Mm-hmm.
the oceans by the equator
Yeah,
are 13 miles higher.
yeah,
than
they are
everything
higher. They pull out. Yeah, when we start talking about oceans, we're gonna go into that. All right, so what we're gonna do is one of you needs to be axis for me and turn, and the other one of you is gonna draw. So who's gonna be axis and who's gonna draw?
else.
You're gonna turn? Okay, so now which way does the Earth turn? First, we gotta figure that out. Which way are we gonna go? Think about it. So look at the US, this will help you. Where does the sun rise?
Please.
Okay, so which way does it go?
That way?
Turn it, let's see.
no,
So look at it this way. Here's the US. Okay, sun's gonna rise here, and then it's gonna go this way, right? Okay, so that way, all right? So if you're looking at it from the top, it's counterclockwise. Okay, so you're gonna try to spin it at a nice steady rate. Okay, not too fast, but gently. Your job is to go at the North Pole, and while she's spinning, draw a line just kind of quickly straight to the equator and stop. Okay, while she spins. Keep spinning. There you go. Don't stop spinning.
Sure.
Woo! You gotta push a little harder. That didn't draw much. Try that again. You're good.
Not finished.
Hang on, I have a different marker. Maybe that'll work better. Where'd it go? Grab a different one for you. Maybe that one doesn't want to work. It worked this morning. Try this one. Here, try this guy. See if he's any. See if he's any better. All right, so you spin nice and steady, and she's gonna have to push hard enough to make a good line, okay? Nice and steady spin. Oh, okay. Okay, you spin. Sort of. All right, so you can still see, even though it's kind of messy. I'll darken this up. So this line went, hang on, not there yet. This line went like that. Is that line straight or curved? It's curved. And which way does it curve?
To the west, to the west, to
To the west.
the
Okay,
west.
now, same thing. You're gonna be turning, and now you're gonna draw from the South Pole up, but you gotta give it a good steady push. All right, do it again. Let's see what we got. Yep, you got it. Just almost. Try it again. There you go. There you go. Okay, that's kind of. So I'm gonna. Whoop. All right, now you're there. All right, I'll darken that. Okay. Went kind of like that. So which way is this one going?
Northwest.
Yeah, this one kind of goes from, it's kind of hard to say. Hang on, where's the black one? These are crazy. So lines from the top went roughly this way. And the line from the bottom went roughly this way. Okay? They go in the same direction or opposite.
Their conversion.
There you go. I'm showing Jack because he's at home and Liam. See? Top one went that way, bottom one went that way. Okay, so this is the Coriolis effect. Now you see it with your own eyes. It's kind of easier to understand. If markers work better, it would be even great. So if you look here, you can see that you got wind going this way, wind going this way. But when you put all the winds together, the global winds together, they do some really interesting things. So you've got three basic categories of these big global wind systems, and there's all kinds of other little small winds within them, right? So we've got trade winds, prevailing westerlies, and polar easterlies. And you also have these things called Hadley cells. This is the circulation that kind of goes like this direction on top, kind of rolls. All right, so what are these? These are the guys that occur at the equator. You got air sinking, and it's warm. Air sinks, warms, and then moves toward the equator in a westerly direction. And then it reaches the equator, it rises again and goes toward the 30 north, 30 south again, cycle complete. What do we call these, Bailey? These are trade winds. Okay, why are they called that? All right. All right, Alex, why are they called that? You're
Because
so
they were
excited.
used by ancient sailors to travel to trade.
Yeah, so yeah,
They changed seasonally.
right. So back in the day, when all you had was a sailboat to get from one place to the other,
Or rowboats.
or rowboats, but really the sailboats are important because they are using the wind. So they use these wind patterns to help push their boats along. They're trade routes. So if you look at historic trade routes, you're going to find a lot of them come right through this part, right? Think about it. Even Columbus and whatnot, he left right over here and he ended up right over here, right? That's where he ended up.
Like how detailed North and South America.
Yeah, this is fabulous. Yeah, I don't even know what that's about.
I don't even know where Britain is. It's God.
It's a blob. So then you have these. These are the guys that occur between 30 and 60, north and south. And they're surface winds. They move kind of toward the poles in a generally easterly direction. So wind is responsible for weather patterns that move across the US and Canada. What do we call these? These are, yes, Piper.
Prevailing westerlies?
Prevailing westerlies. Okay. These flow in an easterly direction. So what you have to remember is
It's where they come from.
it's where they come from that you name them. You don't name them as to where they're going. Now, if you've ever driven anywhere in this metro area along, this is fabulous, Highway 9. Who knows what Highway 9 is? Who knows what road it is? Do you know? It's right outside your house.
Yes.
Yeah. Okay. What's it called outside your house? Do you know what the name of it is? There's an actual name, a street name.
Oh.
I think it's called Alpharetta Street outside your house. Here's the funny thing. Highway 9 goes north to south. It passes from Atlanta all the way up to like Cumming. All right, when you're in Roswell and you're heading south, it's called Atlanta Road because that's where it's going. But when you get far enough down, it changes to Roswell Road because if you were coming the other way, that's where it's going. And the whole thing is like that, up and down, Alpharetta Road, Roswell Road, Atlanta Road, where it's coming from. Yeah.
I think there's a brownie point, when the moves from
Wind. Where is it?
The
blue.
Oh, should say that. Yeah, you got a brownie point. All right. So wind that moves from the what to the what? What direction are we going here? All right, James. West to east. All right. That's what you got to remember for westerlies. They're going west to east. So then these right here, these are, see, I copied it. So there it is again, brownie point. So these are polar something. These go from 60 north and 60 south towards the poles. And in both hemispheres, they're cold. What you got, Caitlin? Polar easterlies. Okay, so if they're called easterlies, then they're going from what direction? Piper.
East to west.
They're going east to west because that's what they're, again, where it comes from. So overall, here's what you get. Trade winds going this direction, right? Then above them, you got the westerlies going this direction. And then above that, you have the easterlies going that direction. So you have all this going on. And then you have these little air masses here. These are the cells they call Hadley cells, where they pick up the cold air and they push it down underneath, but then it gets heated and it kicks over and it goes round and round and round around the outside. And the ones near the equator are actually like thicker, I guess is the way to describe them, taller.
Go round.
So it's interesting to look though, because this pattern is like mirror imaged, right? From top to bottom. And these winds are going to have huge impact on weather systems. They've obviously had huge impact on travel, the way we go from one place to another. So what's a jet stream then? All right. So wind, temperature, and pressure are all going to affect climate and weather, right? And the difference in temperature and pressure create wind that's high up in the atmosphere, really high, like 185 kilometers high. And then that's going to produce something like a jet stream.
So jet stream is the company that produces guys.
I can't hear you. Stick hand away. Kites? What do you mean by that?
Company.
It's a company?
Jet stream.
Jetstream. Okay, that's smart. Jetstream produces kites. Okay, so here's your jet stream. And this is up high, right? Because it said right here that when they're up higher in the air, these differences in temperature can create these things. So despite the jet streams, what kind of altitude, Milo? High altitude, right? Despite it being really high, it has a dramatic effect on weather and it pushes air across the globe quickly and lower air masses can get caught up in it. Now, let me ask you this. So say you take a flight from New York to Seattle. You're going this way. And then you come back, you go this way. Obviously, you're going to gain and lose time based on the time differences, time zones. But usually, it's going to take you a little longer to go this way than this way. Why is that?
Because we're moving with the earth or against it.
Not with the earth or against it.
Don't we?
The Earth's rotation is what's going to cause the time difference. It's a little bit the rotation, but it's mostly the wind. It's the jet stream. The jet stream goes right across the US this direction. So if you're going west, east to west, you're pushing against it. And usually it takes a little bit longer to get where you're going. So that is something else that's going to impact weather. And the jet stream kind of flows like across the top of our country, kind of dips down a little and keeps going and goes all the way across the ocean to over towards like Northern Europe. You good, Lily? Lily looks spaced out for a minute. I'm like, are you okay? All right. So here we go. We have, if we haven't, so when I didn't tell you what that was. So we're going to do fronts now. Okay, fronts. That's a great picture of a front. That's an actual storm front. Fabulous picture of a storm front. Occasionally you see them like that and it's awesome. So a narrow region separating two masses of different densities. What do we call this?
Something that's
Parker.
in big trouble.
Up front. Parker's right. Okay. Something what?
Something that's about to get squished by two different masses.
So the density differences can be caused by differences in pressure, temperature, and humidity. Okay, so if one mass has high humidity and the other one has low humidity, which one's more dense?
High.
High, okay. If one mass has high pressure and the other mass has low pressure, raise your hand, which one's going to be more dense? Drew? High, okay. Bailey, I'll give you this last one. So if it has higher temperature or lower temperature, which one is going to be more dense? Correct. Okay. So this is what's going to cause these masses, when they come to each other like this, either they're just going to stop, or one's going to go under and the other's going to go, yep. The more dense one is going to go under. So we tend to, yeah, can't go over it. We can't go under it. We tend to think about hot air rising, but that's not really what's happening. What's really happening that makes warm things go up? Yeah. It's the cold air sinking, going beneath it and displacing the hot air and pushing it up. So when you see like the warm, moist air rises to make a cloud, it's not, there's no magical force making it rise. It's not getting sucked from above. It's the colder, denser air come down and displacing it, pushing it out of the way. So we have different types of fronts. We have 4 major types of fronts. We have cold fronts, and on a map, they draw them like this. And we have warm fronts, and they draw them like that. Stationary fronts. So look at it this way. With a cold front, you've got warm air here where you're living. This cold front comes in, and it's going to push the warm front. And what's going to happen here? Which fist is going under, and which is going over? Cold front comes in, it hits this warm area. What's going to happen? Bailey. Oh, no, I was looking at you. Yeah. Right. So if you've got, this is where you live, everything is cool. I should use something you can see. Yeah. The bottle and the can. Yeah. So if this is where you live, cold front comes in, it's going to push underneath, and that's your cold front coming. Now your warm front coming, it's going to come here and it's going to do what? It's going to cause this kind of movement, right? And then you have a stationary front where they just sit there and stare at each other for a while. And then you have occluded fronts, and those are a little different. That's when you kind of have some action going on. And then they have these other things too. Squall lines, through or outflow boundaries. You might see them on maps. Don't worry about them too much. What you worry about is really when you get cold and warm fronts, because that's going to have the most impact on you. So what would this be describing? Cold, dense air pushes warm air up steeply. As warm air rises, it begins to cool and loses its moisture. And then it's a solid blue line with blue triangles pointing in the direction of this front's motion. Chloe, what kind of front are we talking about? A cold front. And this cold front is going to bring us clouds, showers, and thunderstorms. Now, how about this one? So this occurs when warm air displaces cold air near the surface. The air ahead of the warm front moves slowly because of less land friction and can gradually push the air up. Solid red line with semicircles, and they point towards the front's motion. And you can get clouds and precipitation. Milo. That's going to be your warm front. Okay. Any of these situations, when you've got one front smacking into another, can cause changes in your weather or storms, right? So there's your warm front. Now this one, you got 2 similar air masses, they collide. Sometimes neither can advance or overtake the other, and it results in what we can call a stall. So Parker, that's a stationary front. And your solid blue line with alternating blue triangles and red semicircles. So what you get here is this is pointing in the direction of this front, and this is pointing in the direction of that front. Yeah.
It's not solid.
No, it's not really. Kind of stopped off, but I think it usually is a solid blue line. I don't know. Maybe I stole that image from somewhere. Okay, how about this one? Your warm front gets wedged between 2 cold fronts. The warm air gets pushed upward and rain is common on both sides of the cold air border. This is the purple line one. Milo?
I don't know how to pronounce it, but it's gonna start with an O.
Yeah, there you go. Occluded. It's your occluded front. Occluded is a good word. So here's another one to think about. Occluded. What is it called when your teeth don't mesh correctly? You may have heard the orthodontist use the word. Do you know what it is? That's one. Yeah, there's like a technical term. Do you know it?
Occluded.
They say it's malocclusion, right? So when your teeth don't fit correctly, they don't fit like that. Like the ridges on your molars are supposed to kind of click in place like this. And if they don't, that's maloccluded. So occluded would be that they do what?
Stupid.
In place correctly.
Yeah, they fit together.
Occlusion can mean hidden from sight. as well.
Yeah, yes, it can be. So you get this kind of wedging going on in this. So pressure. How does pressure affect the weather? This gets interesting. Okay, so your rising air is associated with some kind of pressure, and then your sinking air with another kind of pressure. So what do you think goes with rising pressure? All right, Piper.
Rising air or rising pressure?
Rising air is associated with what kind of pressure? Piper. Rising, okay. All right, and who wants to do the other one? Then it's going to be Bailey. Okay, so, now think about this. This one is kind of weird. You have to really think. Why would rising air be associated with low pressure? Bailey? Okay, and Drew, how about this sinking air and high pressure?
Get the more pressure there is.
Okay, so this one is a little, like I said, a little inverse too. And this one can be confusing. So you got to think about it this way, all right? When you want to think that low means down, right? If it's low pressure, it must be going down, but it's not. It's the exact opposite because it's less dense. If it has low pressure, the molecules are more spread out, it's less dense, and it rises. And if it has high pressure, molecules are closer together, it's more dense, it sinks. So you can't let the high and low of pressure, you can't think about it like altitude because it's going to be the opposite, right? Does that make sense?
Yeah.
Not sure. So if you've got dense air, what kind of pressure are you going to have in your dense air? High pressure. Why? Why are you going to have high pressure if you have dense air? More molecules together, right? It's all squashing in there. Great. Okay. And how about if you've got low pressure? What kind of density are you dealing with your air? Yeah, it's lower density. So think about it like this. You ever have one? What's an example of something that does it? Let me think here. You ever had one of like something that's like a vacuum? I've seen jars. Oh, a plunger is a great example. Okay, so if you stick a plunger down on something, right? And then you pull up on it, you're pulling it up, you're pulling all the air inside of it up, but you're also spreading out all of the molecules because what was caught in this little shape is now spreading this way, right? So you're increasing the volume there, which is decreasing the pressure. So the same thing's going to happen with air. It'll sink if it's got more density. So your rising and sinking air combined with Coriolis effect result in rotating high and low pressure systems. So in a high pressure system, air is what? Bailey. Okay. So when it finally hits the surface of the earth, it spreads out, pushing everything away. So it's sinking because it's dense. That's correct. All right. So when it gets there, it's going to kind of like if you dropped a pile of sugar, it'll go, right? Same thing. And in this case, what you're going to get is clear skies because as that high pressure comes down, it's going to clear everything out. You can think of it like this. Say you've got sand on the table, okay, and you've spread it out pretty evenly. And you blow into the middle of the sand. What's going to happen to the rest of the sand? It's going to spread out. What is the difference between what you're blowing and what's there in the environment? Think about it.
Nothing.
Yeah, there is. Think about pressure.
How dense it is.
So if you're going that air, you're pushing it out at a greater speed and at a volume where you're increasing the pressure. If the air pressure coming out when you blow wasn't stronger than the environment around it, you wouldn't be able to inflate a balloon. Think about it. You've increased that pressure, right? So when you put a stream of increased pressure down in the middle of that table full of sand, that pressure, that high pressure, it's just like a high pressure system. It pushes everything out. So if the pressure's high, it's probably going to be a good day. What's the pressure on the, can anybody see it? What is it today? It is, okay, if I don't throw it, where's the pressure? Okay, it's 30.37 inches of mercury, 30.37. Who's got a phone? Okay. What is the average air pressure for, look for Atlanta, because you need to know elevation above what? What do you think?
Sea level.
Sea level, that matters greatly. Elevation above sea level matters. So somebody tell me what's the average air pressure
For Atlanta.
for Atlanta? Uh-huh.
Uh,
What'd you find?
30.09 in HG.
Yep, that's mercury. Inches of mercury in HG. 30 point what?
30.09.
30.09. So what does it say now in front of me? 30 something, 30 point. What did it say? Shoot, 30.37. So it's a little higher than the typical. And it's nice, right? Now, if it dropped lower, the weather won't be so pretty. And that's where you get a low pressure system. So as air rises, it creates space beneath it. And that's going to be filled by what kind of air? What kind of air is going to come in and fill it?
Temperature wise?
Well, just describe it to me. What would you think? It says, as air rises, it creates space beneath it that's usually filled by what kind of air? Truthfully, it's kind of backwards the way this is worded. Denser air. Yep. What else? Denser. And anybody else want to throw anything else? Alex?
Colder.
Colder.
and
James, did you have something else?
Sure.
Oh, and higher pressure. Okay. Yeah. So colder and denser is exactly what we were looking for. So it's really not that the air rises and creates a space beneath it, even though this is technically how it was worded. What's really going on?
It goes, cold goes down, creating space above.
Correct. The cold comes down and pushes the hot up. It's displacing it. This is how you get clouds and rain. All right. So weather and data analysis. Now, this is what you're going to be doing all week. Okay. So we have different ways of measuring things. How do we measure temperature? With what? Let's see. Oh, Sky, give me this one. How do we measure temperature? With what? It either has mercury or alcohol in it that expands when it's heated. How do you measure? With a thermometer. Yes. So we measure temperature with a thermometer. What do we measure air pressure with? Air pressure. Drew?
The barometer.
Okay. There you go. And let's see. What do we measure wind speed with?
Wind socks.
No. Wind speed. Bailey. No. Anybody know? This is another one that has a Greek root at the beginning. Do you know?
Anemometer.
Yeah, anemometer. Yeah, anemos means what?
Wind.
Wind in Greek. So anemometer is how we measure, and that should be 2 right there. I caught that one. So these use rotating cups to measure wind speed. You see ours on the roof? It had little cups. They're about the size of, like, I don't know, not quite a tablespoon. And they're lights, very lightweight. So as the wind catches it, they spin and it measures speed that way. The last one, air pressure. Wait, no, sorry, that should say humidity. Ooh, I wrote that wrong. So humidity, what measures humidity in the air? Alex?
Is it a hydrometer?
Close, it's a hygrometer. Okay, what's hydrometer for? Do we know?
Measuring various things in water.
Yes, so it's basically, I'm gonna put that in there, fix that. It's basically about, let's see, like the ratio of something to water. Can somebody give an example of when you might use that? Drew?
Salt in the ocean.
You can do it that way. Can you think of another way to do it? Another thing you might use it for? Milo?
I use it to measure the humidity in my bearded dragon tank.
Oh, that's excellent. Okay, that's probably a hygrometer. Yeah, but yeah, you're right. That's good. All right, anybody else have another thing you might use it for, James? Chlorine in a pool. These are all good. Okay, so we actually, too fast. We actually have a hydrometer in this house. Anybody want to guess what we use it for?
Sewage.
Nope, not sewage.
Water bubble?
Nope. So my husband does, he'll do homebrew, like he can make beer, but he also makes cider. We do a lot with cider. So what do you think he's measuring in the cider? What's going to matter? Do you know? What do you think, Piper?
Humidity?
Not the humidity. Let me tell you. Okay, he measures it before he ferments it. What do you think? What do you think he's measuring for?
Sugar.
Drew? Yeah, sugar. It's measuring the sugar content because the sugar content will impact the alcohol percentage at the end. because that's how fermentation works. Right, Piper? Yeah, all right, so let's look at this one. That was all lower level data.
Sauce
It's
again.
got a big old Eisenhower dollar stuck in here. Yeah, fish guts, yummy.
See, star guys.
So we have to get data from the upper level too, because if we don't, we can't be accurate. So we have weather balloons that have sensors for temperature, pressure, and humidity. Do you know what they're actually called? Anybody know, Milo? Yeah, very good. Radio sound. Yeah, you're close. There you go. So do you know that you can actually go collect weather balloons? Yeah, my husband has a friend who does this. You can follow, it's public data, where they've launched and like roughly where they land, and you can go find them. He goes and hunts them like geocaches. He pulls them out of trees and off the ground because they crash somewhere. They pop, usually when they get up high enough, they come down and they crash.
Can you smell them?
I don't know. I know you can turn them back in or you can keep them, but weirdness.
Like,
Scrap
isn't there
'em.
like a big piece of technology? Can you steal
Mhm.
them?
It's got little bits, not huge technology. So what do we have that reflects, that has radio waves that get reflected back? What do you think this is?
Radar.
Radar, Satellite, okay. So we got radar, you get there. So your radar, yeah, I see you. So radar is what's getting weather radar. So that's when you see, you ever watch the news and it looks like an old army video. There's like a needle and it spins around on the forecast. You can see this, like it wipes it clean and keeps going around and around. And you can see the storm, the colors that they're using to represent it moving around and around. That's the radar going. So how about this one? It says waves change frequency at a distance between a target and the observer. So what is this one? Who wants to go? Alex, what is it?
Radar blue shift.
That red and blue shift is what we're getting for, but the Doppler effect is part of the red and blue shift. So you remember when I was talking earlier about the big effing, that was big effing Doppler was the joke when I was a kid because it was ridiculous. It was ridiculous. So yeah, what's the Doppler effect? Can somebody explain it? Anybody know what it is? There's a really easy example. What, Alex?
A good example is ambulances
That's a great one.
as they're moving around.
Mm-hmm.
So it has to do with the waves
Uh-huh.
becoming either more spaced out or more squished.
Right.
as Either
Mhm.
moving towards you.
The sound
or
waves, yeah.
Moving away.
James, were you gonna add
It
something?
also works with lights.
Yep. So
It-
ambulance, or let's think about this, a train. Okay, let's think about a train. If you're standing there and you're watching the train and think about the pitch of the sound, okay? It comes from here, it passes you, and it goes that way. Describe what happens to the pitch, Drew. Yeah, so up here on this side, before it passed you, here and here, where is the pitch in relation to, if it's over here, where's the pitch in relation to you, higher or lower?
Goes low, high, low.
It goes the other way.
High, low.
High, it goes, no, right? And that's because from where you are, the sound waves are,
Compressing.
yes, they're getting compressed as they come to you or getting spread out as they go away from you, and that changes the sound. Same thing happens with Dopplers, and this will be, we'll talk about this more, especially in physical science, but the Doppler effect also explains why stars, why you can tell the universe is expanding, because stars, as they move further away, their color changes. There's a red and blue color shift, and it has to do again with the wavelength of light. Is light, so light's a wave, right?
It's a wave and a particle.
It's a wave and a particle. Perfect. Yes, it's both, behaves both ways. It's weird.
Yeah, I love
The
it.
only kind of energy like that. All right, and this last one, visible light imagery, digital photos, infrared heat, and water vapor imagery data. What are we getting that from?
Satellites, cameras.
Yeah, satellites. That's perfect. Yeah, you ever tried to look on Google Earth and something's just covered in clouds and you're like, yeah, they have to fix that picture and come back and do another one on a day that wasn't cloudy. It's gotten much better now, but it used to be there were patches of it that were just clouds. What am I looking at? What's the point of this? So weather analysis and prediction. So we've got a kind of a model that is going to record data for a particular site. Then we have two other things that can show up on maps. One shows lines of equal pressure like this, and one shows lines of equal temperature like this. So this first thing I'll tell you, this one's a station model. Basically, it's this. It's what's coming from your station. It's that data. What does this remind you of? Anybody? Does this look similar to anything, Piper?
Something you studied on, I forget.
I forgot its name. Chloe.
Topographical.
Yes, it looks like a topographical map. Exactly. And it's the same concept, except it's with pressure. So remember with the topographical map, it's got, when you get closer and closer in a concentric circle, the elevation gets higher and higher. In this case, what you're dealing with is pressure. So look right here. It's 1024, and then this next one out is 1020, and then 1016. So it's getting lower. So you've got really high pressure and really low pressure coming together right there. And you see where it's all compressed because they're smushing together. And then this you're probably very familiar with. You've probably seen this, right? They show this on the news or whatever all the time. This shows kind of where your general temperature is going to lie. So do you know what you call these lines here? Anybody know what they are? These are isobars. And then anybody know what they call these?
Thermobars?
Close. Isotherms. So it's the ISO we're dealing with in this case. So isobars, isotherms. Shows you where the pressure and temperature are the same. All right, so how do we do short-term forecasts versus long-term forecasts? So they say if you're about Monday, Tuesday, let's say it's a Sunday, Monday and Tuesday, you're about 80% accurate as you move out, right? And then Wednesday, Thursday, Friday, you're getting less and less, 50% accurate. And then so you're not very accurate at all down here. Right? They're just guessing. They have no idea a week. They put those 10-day forecasts out. It's so fun to watch them change. I get really excited when it's going to snow. I really like the snow. I don't want to live somewhere it snows all the time, but it's like a treat here, right? And I can stare at it for hours as it falls. I get captivated by it. It's so pretty. I'm a beach girl. We didn't get a lot of snow. So it's always fascinating to me. So I'll watch that 10-day forecast and it'll be like snow, rain, ooh, move to Thursday. Nope, Friday. They don't know. It's interesting. And that's because it's so complicated. So the key to unlocking the weather forecast puzzle is to understand that the atmosphere acts like what? Think about this. What could this be?
Blender.
Like a blender. So what's the atmosphere composed of?
Yes.
Gases. Okay. So what does it act like then? James? Yes, it's a fluid. Good going. So if you can think of it like a fluid and it's flowing all the time, then you can apply your concepts like temperature, density, and pressure to understand it. So if you think about the way water moves, okay, how does temperature affect water? I've told you guys before, when they open that dam, what kind of water comes pouring into the river as far as, yeah, it's colder, right? Because it's coming out of the bottom of the lake. So that water goes where in the river? It goes to the bottom, right? And then as it goes to the bottom like that, the water on top looks like it's flowing like this, but the water on bottom has high pressure because it's coming out of the dams. It's whipping along the bottom. What were you going to say?
I'm just gonna
Oh, just going to answer that. Yeah. So if you can apply concepts, how does water behave? How do ocean currents behave? How do rivers behave? Then you can use those same concepts and apply them to the atmosphere. So back in the day, this dude, he's so cool. Look at his hand-drawn map. Good for him. He's probably on the news like this. At least he didn't have green screen fails. So anyway, back in the early days of weather forecasting, you had meteorologists simply observe what was going on, compared it to the last couple of days, and then tried to predict future based on that. Wow, that's going to be rough because last week were our temperatures higher or lower than today?
Lower.
They were way lower. Yesterday was it a record? I think it was a record or close to a record. These 2 or 3 days we're in right now that are like ridiculous warm. Ugh. Right?
Welcome to Georgia.
Welcome to Georgia. Yep, Georgia season change is always fun. So something else to consider about weather is the geology of your area, the topography of your area. So where I went to college in Roanoke's like a bowl. There are mountains all around it, and then it's in the middle. So if you got a cold air mass that made it over the mountains, it's stuck. It was hard for it to blow out because it's more dense and it's just sitting down there. The warm air is just blowing above it. So weird things would happen with the weather because of that. So you can have digital forecasts, and this is what we do mostly now, these high-speed computers. And what they're going to do is they take all the data from all these different sources, and then they integrate it. Kind of like Waze. We talked about Waze being like an integrated type of a map because it uses what? It uses like Google Earth, right? And it uses other people. It's open source, right? Everybody can add their own data to it, and it uses all that and puts it together and can tell you like where traffic jams are and whatnot. So all that comes at one time, and it can analyze it all and put it together, which is great because the more sources you have, the better. So analog forecast, this is going to compare current and past weather patterns to generate a forecast. Where did you see an analog forecast today? And where did you see a digital forecast today?
Farmer's Almanac.
Hang on, James,
All that.
which one was that? Analog or digital?
Yeah.
Very analog. Yeah. And how about the digital one? Where was that? Drew? Yeah, right here or pretty much anywhere. If you looked at forecast anywhere, especially like this is just straight up reporting data. But if you looked at the predictive stuff, the forecast stuff, anywhere you see it on TV, that's all digital stuff. They're using all kinds of sources and compiling it. Now, when next time it's going to snow, and they're saying it's going to snow, watch the weather, guys, because there are different models. Watch the local weather, even though I don't usually watch local TV. I watch the local weather because those dudes get super excited and it's really entertaining. Like they're super excited because they love it. When the weather's coming, they get, whoop, here I am. I get to be the star, right? And there are different models they can use to predict what the weather's going to be. So some models are going to rely more heavily on pressure, others on temperature, others on satellite data, others on Doppler. So they'll be like, this is the European model, and this is the whatever his name was model, and they'll pick their favorites and then they'll compare one to the other. It's interesting. So, and now for the weather forecast, what? It'll be sunny unless it rains, because this is long term. They don't know. It's hard. It's really hard. And everybody gets frustrated with the weatherman, right? You're like, dude, why are you never right? Well, because it's super complicated. So the further into the future you look and try to predict the weather, the less accurate your forecasts are going to be. There's just too many variables, way too many variables. So, you know, you could have an air mass move in, you can have pressure shift from one to another over an area because an air mass moved in. You could have a volcano erupt. That would impact the weather. You could have a hurricane form in the Atlantic and start moving its way up, right? All of these things impact the weather, and it gets very, very complex. So what does this even mean? What does this even mean? So don't answer unless you've raised your hand. All right. So if they say it's 80% humidity, they're giving us relative humidity, right? Okay. So don't answer. We're gonna watch it. So what does this even mean? It's not really a question to answer out loud. So if they say you have a 50% chance of rain, so you got people, wait a minute, wait, don't answer. You got people going, oh, they said it was only a 50% chance. Why is it raining? They're never right. And then you got people that are like, why isn't it raining? They said it was a 50% chance. They're never right. So how does this work? All right. This TikTok became like super, it went viral. And here's why. It's interesting.
What is something you found out
What?
last you should have known earlier, but you just didn't?
I thought 100% that when they said that there's a 30% chance of rain, that it meant that there was a 30% chance that it was gonna rain. I never, ever knew that it meant that there's 100% it's gonna rain, and it's gonna be in 30% of your area. So in a way, there's a 30% chance that you're gonna get rain, but it's going to rain. It's only gonna cover 30% of the area. So like if it says 100%, it means your entire area that you're asking about, your zip code, whatever, like it's gonna blanket the whole thing. Am I the only one who didn't know this, or they were grumped? Like I found that out this
Grumped.
year.
She's definitely not the only one, because here's some of the comments that she got. I found that out right now. I'm a meteorologist and this isn't true. Oh, I thought it was I love this one's my favorite. I thought it was how heavy the rain was, like 100% max rain and 30% was like a drizzle, right? I love that. That's a great comment. So her little TikTok video went nuts because people were all like, what do you mean that's not what it means? Because most people actually don't get this right. And here's why. It's more complicated than you think.
All right, guys, let's talk things out. I'd wait for my husband to get home because I have a smartphone. Anyway. So here's our rain in the past 24 hours. Even worse than we thought. Different meteorologists use chance of rain to mean different things. So you have to ask your local meteorologist what chance of rain means to them. However, check out the bits from these nice meteorologists who explain that generally, and this is the direction that the industry is moving, a 1 to 2 day forecast is a coverage for. So if they are saying for 30%, they already know that close, that is going to rain, and they're saying that it's gonna cover 40% of the area. They're out, there's no confidence, they do that top multiplication thing, whatever. But generally, the close forecasts are coverage forecasts. So part 2 is next. You don't have to like for it.
So she went, her little thing about what do you know, what did you just learn that you should have known forever? This first one went completely viral. People commented all over it because people don't understand. And then she comes back with all the answers she's compiled in the last 24 hours and reports back. So she said they do that little pop multiplication thing. All right, so here's what she's talking about. This is pop. So it is percent of probability, of precipitation, pop. So what it does is it's describing the chance of precipitation occurring at any point in your selected area. So how do they get to that? So what they do is they use a formula that's pop equals C times A. C is the confidence that precipitation will occur somewhere in the forecast area. Okay, the forecast area is whatever area that meteorologist is covering. So if he's a TV meteorologist, he's probably covering what? What do you think?
The US.
Nope, probably not, unless he's like on CNN or Fox. If it's one of our guys, what's the guy, Chesley McNeil? What's he covering?
Like, no, like town, city.
Yeah, he's covering the viewing area.
Wow.
Wherever that TV station is broadcast to, the viewing area. So like the Atlanta stations cover Atlanta, all of the suburbs, a little into the mountains, but they don't really cover much about Savannah, right? Wherever they're reporting news is where they're going to cover for the forecast. All right, so C again is the confidence that precipitation will occur somewhere in that area. And then A is the percent of precipitation that area, that's what the A is for, will receive measurable precipitation if it occurs at all. So what percent of the area is going to get any kind of measurable precipitation if it occurs at all? So they do this by doing your confidence, how confident are you the precipitation will occur, and what percentage of the area are you confident is going to get covered with precipitation? And then this is going to equal your POP. So in this case, they're 100% confident it's going to rain, but they think it's only going to cover 50% of the area. So this is going to be 50%. So when you do math with percents, you treat them like what? Decimals, right? So 0.5 is what percent?
50%.
0.8 is 80. That's easy, right? Think about it like money, 50 cents, 80 cents, right? Okay, so most of the time, the forecaster is expressing a combination of degree of confidence that it's going to be precipitation, and then aerial coverage. So if your forecaster is only 50% sure that precipitation will occur and expects that if it does, it will produce measurable rain over 80% of the area, then the equation goes like this: 0.5, that's your 50%, times 0.8, that's your 80%, and what's your chance of rain? 40, right? Okay, let's say your forecaster believes there is a 20% chance of rain over 60% of the area. What is the chance of rain percentage going to be?
Just realized, I think, is that supposed to be Ariel? I think it's spelled wrong.
No, area.
No, Ariel up there at the top.
No, that's right, meaning area. You're thinking the other one with an I. Is that what you're thinking?
Yeah.
That's like if you're looking at it from a plane, because that's just what aeronautics. It's a weird one. So anyway, I was saying he is, what I say, 20% sure that it's going to rain and cover 60% of the area. So what are we multiplying, Bailey?
12%?
Yeah.
Yes, because we're multiplying 0.2 times 0.6. 2 times 6 is 12. 12%. All right. So what if he is 30% sure that it's going to rain over 30% of the area?
9.
Wait a minute. Raise your hand. What are you going to say, Bailey? 9. So what is that? What percent is that?
9%.
3.3 times 0.3. 9.
0.09.
0.09?
Well.
If it's, he's
30.
30% sure it's going to rain over 30% of the area. 0.3 times 0.3 is 0.9.
.0.
1-4.
There you go. The answer is always 4, right? Anyway, this is how they do those sort of calculations. So if you're saying if he says, I'll hold this up so you can see it. So if he says it's going to rain over 30% of the area, and he's, or 30% confident it's going to rain over 30% of the area, 0.09. So you have a what percent?
9%.
9%. There you go. Yeah, you wouldn't say like an 09, you just say 9%, right? 0.09 is 9%. All right, so there you go. So that's a 9% chance of rain. So would you plan an outdoor picnic?
Yeah.
Yeah.
I would for that. Would you plan an outdoor picnic? Let me go back one more. Would you plan an outdoor picnic for if it was going to be 50%? Maybe. Where's your threshold?
100% simply out.
60,
Uh,
100? Say you're hosting an outdoor dinner party for fancy guests. Where's your threshold? 30?
1.
Mm-hmm.
14.
14. Uh-huh. We had when Drew turned, I think it was when you turned 4, we had rented a picnic pagoda. And I think it was a 30% chance of rain the night before. And I was like, oh, we're good. We're going to go. And then the next day it was 55 or something. And I thought, oh, no, I'm not going to do that. So what I did was we moved it to the house and then it poured and we were having our gutters replaced at the time. So there were no gutters on the house and rain was sheeting off the house. It was a mess.
End up raining wait, which?
That was the Scooby-Doo one. I think you were 4, 3, 4. You were tiny. It was a mess. So anyway, let's look at these real quick and make sure that you guys understand these answers because we're about done, but we're a smidge early. So meteorology is the study of atmospheric phenomena. Now, weather is the current state of the what? Atmosphere. What's lithosphere?
Stone.
Yeah.
Similar to the geosphere.
It's similar to the geosphere, but without the water included, right? Mm-hmm. It's the land.
Right, geosphere.
So this one's right. Long-term variations in weather for a particular area make up a climate. How about what's wrong with this one? The tropics are hotter than the poles because the sun strikes this area more
Get rid of the and-
directly. Why?
Because it doesn't hit it directly, it's indirect.
It
it's
hits
the
them more
angle.
directly, right?
It's
And again,
Yeah.
why is that?
tilt to the axis.
Axis,
But
Earth's
the reason that
axis.
the tilt to the axis is important is because of the angle at which the atmosphere scatters light back
Right.
when it is at an angle.
Right. So, and I'm going to show you something after these too, because I have something else that I did with the other group that I think would be fun for you to see. So if you've got this large parcel of air that takes on characteristics of the area over which it forms, that's the air mass. It takes on characteristics of where it forms, but then what happens as it moves?
It changes.
It changes
It
its temperature. and
changes.
It changes to reflect what?
The new one.
The characteristics of the land below it. And then obviously maritimes over oceans, we talked about what that means. Air mass travels over land that has, when an air mass travels over land or water that has different characteristics of those of its source region, it undergoes air mass modification. That's what we call that changing. Okay, this one kind of self-explanatory. It all goes together. I'm gonna show you this other thing too. Let me, go ahead, move. I hate it when it gets stupid on me. There we go. All right, so cold dense air that displaces warm air, forcing air up is a cold front. Narrow region separating the two was a front, Parker told us earlier. Then your warm front is when your warm air displaces the cold air again. And when that happens, that usually means that it's got a lot of pressure, remember, because if you've got warm air, the only way it can displace cold air is if it has higher pressure, because the cold air is typically going to do what?
Thing.
It's going to sink. So you have to have something with higher pressure to push it out of the way.
So someone.
And then our stationary and occluded
Yeah,
fronts.
please.
So let me show you something that we did with the other class that is pretty cool. That's yours. This no, that's not it. That's lab. Too many things. This is it. All right. So where is it in here? So theirs was slightly different than ours. So we talked about with them Oh, gosh, everything's in front of everything. So then we talked about atmospheric energy. What's the, what type of energy is there in the atmosphere typically?
Static.
It's a good one.
Potential gravitational.
Gravitational, yeah. What else? What do you, James, did you have something to add? Heat. Okay, that's what I'm looking for there. So heat in particular, where'd that come from? So heat in particular, where's heat coming from? So we talked about is light a particle or a wave, and you guys know this, right? You guys know that it
Yes.
can behave as both. Give me an example of light behaving as a wave. Where's a way that you can see that that's what's happening? James.
Visible light through the atmosphere.
Okay, that's one way. All right, what else? What's another way you can see it? The reason you're seeing that visible light through the atmosphere is because it's doing what? It's reflecting off a surface back to your eyes. So that's how you know. Okay, and then Alex, what were you going to say?
Another way to see that light is a wave is I don't remember what it's called, but it's an experiment with slots cut in a piece of paper.
Yeah. Mhm.
I think I don't remember what it's called, but there's two. Like,
Yes.
And it produces the bands that are
Yes.
characteristic of waves.
Yes.
Wave cancellation.
So we actually do in physical science next year, we talk about polarized light, and that's basically when, so you've got waves going all different directions, and the polarized light knocks some of them out, so it only goes one way. And you can think of it, they give an analogy of a fence. Like if you have a fence and the slots are like this, the waves that go like this can get through the slots, but the waves that go like this can't get through the slots. So yes, it can behave as both. How about when you see like hot air coming off the road and you get that bending of the light? Okay, how about a particle? How else does it act as a particle, Drew? Laser pointer. Okay, who else has one? Light as a particle,
Lightning.
Okay, there, it's a good one. Light. All right. So also you can think about if the light shines on the hood of your car, how is your car going to feel? Warm. Is that a wave doing that?
No.
Explain.
Well, technically, it's
both. Yeah, but what aspect of it is causing it's the particles hitting, right? That's what's causing that. So keeping that in mind, skip this one. You guys don't need it. This is what we're dealing with when we're talking about energy in the atmosphere, electromagnetic spectrum. So this is right here. This is the electromagnetic spectrum band, basically part of it that we can label. Do you see that little tiny spot right there where they're not touching?
That's what we can see.
That's visible light. Yep, that's the only part of it you can see with your eyes. Now, as we go this way, okay, somebody tell me what is wavelength? How do you define wavelength? Do you want to try it, Drew?
There's two different terms. I don't know for which, but one is how high they are. The other
That's
Huh?
is very good.
Yes, so amplitude is how high, right? And then wavelength is how far apart they are. And you can measure, for example, you can say like from the tip of this one to the tip of this one, there's a distance. Or you could say the bottom of this one to the bottom of this one. The distance that you're talking about is your wavelength, okay?
I don't remember the name for the height, but the other one is troughs.
Yeah, that's right. Troughs, which we'll do a lot of that next year. So look down here at the wavelength and look over here at the wavelength. Where's the shorter wavelength?
Gamma on the
It's
right.
over here. And then the longer wavelength over here. All right, this is stuff like radio waves, which can be huge, like building sized waves, huge waves. And then over here, you've got these much smaller ones. These are really tight together. So where they're really tight together like this, you've got higher energy. Now, frequency. Do you know what frequency is with a wavelength?
Frequency is. Sorry.
Go ahead.
Frequency is like how often. I don't know.
You're there. How many times in a unit of time it passes a point? So here's your point. And how many times does this part pass the point? Is it passing it very fast? Is it passing it slower? And that tends to go with your wavelength. It's an inverse thing. So if your wavelength is short, your frequency is high. See, if this was your point right here, it passed through it a whole lot faster than it would this point here, right? So if your wavelength is long, then your frequency is low. And the frequency is going to equate to your energy. So look right here. We can't see ultraviolet, right? It's just kind of on the edge. I mean, real, true, like into the spectrum ultraviolet, we really don't see. What does ultraviolet light do to you if you're in it too much?
Cancer.
Cancer,
Causes cancer. What kind?
sunburn.
Yeah, sunburns. And what kind of cancer does it cause? Skin cancer. Okay. Look at the energy. All right. This high energy wavelength is pounding at your skin and doing damage to it. That's what's happening. Your cells are going, "Ugh," and they're multiplying all wrong because they're getting beaten up over here. But over here, there's radio waves everywhere right now. We are surrounded by radio waves. And when we turn the microwave on, does that bother us?
No.
No, because you got this nice big low energy, slow moving wave. All right. So this shows light as a spectrum. All right, keep this in mind. I mean, electromagnetic spectrum and light as a wave. This shows light as a wave. Now remember, our visible spectrum is right in here. We can only see this tiny bit. And your lowest energy, your long wavelength, your low frequency is red color. Infrared is just past that. Infrared means lower than red. Your violet, if this is your Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. Your violet is your highest energy, right? Short wavelength, high energy, high frequency. And ultraviolet would be just beyond violet, right? So you have just below red, just beyond violet. What do you use infrared for? What do we do with it? Do we use it for anything, James? See, heating, yeah, that's a good way. What else?
Heating.
How about remote controls? Do you have a remote control? You have to point at something, right? So you got infrared. We use it for things like that. And we use radio waves, obviously, for radio. We use microwaves, all that kind of business. X-rays are here. You know what we use those for. What do gamma rays are right here too? What about them? Yeah, yeah, sort of radioactive stuff. That's where this is coming from. Okay. So keep this in mind, this bit right here about where the energy is, how the wavelength, whether that wavelength of that particular, because when we see this light, like this light in here that we're seeing everywhere, it's full of all these colors, right? And things are only reflecting certain colors back to us, but some of these become more visible at certain times of day. Yeah.
One interesting thing about infrared is that while it goes through most substances, like it goes through walls, it does not pass through glass.
Really?
Glass stops infrared.
I never thought about that. What were you gonna say? You were gonna add something, I thought. You're over there in the kitchen. He's like, yes. So,
What pass through water?
Yeah,
but not glass. Why not?
I don't know.
Oh, so that has something to do with the reflections. They can't pass through mirrors.
What were you gonna say?
Oh,
That could be because it's amorphous, right? So what's the advantage of an IR remote, or why would you want it?
To turn stuff on remotely.
Yeah, well, there you go. Do you want to take a second? You're back there in the kitchen, the IR stuff. What do we have in the room that's IR, for example?
All the remotes for all the equipment.
So yeah, everything, it just,
For the TV,
yeah, the TV. What's the TV on?
it's a higher radio, it's a radio frequency. They call
There you go. So there we are. All kinds of different stuff. Now, keeping that in mind, when you've got sunlight coming to Earth, it gets scattered by particles in the atmosphere, right? It's going to hit stuff, particles, dust, whatever. Those things that we called lithometeors, right? And when it hits them, or water too, water particles, when it hits them, it's going to get scattered because that's what happens to light. It gets refracted, reflected, and scattered about. So we have a type of scattering called Rayleigh scattering, okay? And what happens with that is when the light, the white light, which is all the colors, right? When that hits a particle, the Rayleigh scattering, there's different kinds of scattering, but the Rayleigh scattering is particularly for the wavelength of blue light, and it's going to cause it to scatter in a sphere shape. Okay, so when people ask you, why is the sky blue? That's why the sky is blue. So you've got blue and, son of a gun, as I keep doing, you've got blue and violet light. They've got the shortest wavelengths, and red light's got the longest. So your blue light is going to get scattered more than your red light. So that's why the sky is blue during the day. Now, when the sun is low in the sky, when your angle is lower, right, it's coming up over the horizon for you, or actually you're turning towards it, then like at sunrise and sunset, that light's got to go further to get to you. Think about it. If it's light in Savannah, daylight, the light's up. What color is their sky when the sun's up? It's blue. But if I can see it just starting to rise, that light's just starting to reach me, that's the light that's traveled even farther. So that's going to be, remember the red was on the end of the spectrum over here with the big, long wavelength, right? It can travel farther. So that is going to get to me first. So what color is the sky going to appear when I'm looking at the sun in the distance? Reds and yellow. Yeah. And then you get the water in there that can reflect and refract, and then you get slightly different colors. So you don't see the blue light, it gets scattered, but the red light isn't scattered very much. So the red sky appears in the morning. So that's how you get sunrise, sunset colors. And that's why your sky is blue during the day. So when people ask you, why is the sky blue? It's called Rayleigh scattering. You can just say Rayleigh scattering and look super smart. That'd be fun to see someone's expression if you just randomly said that. But that's why you have blue sky during the day, and then you get red when the angle is lower. Because you can see right here, you can see how this red one is going a little farther. Yeah, that's why. So we talked about that too. But I figured I would share the why is the sky blue business with you guys, because that's interesting. Okay, so progress reports. Some of you still have some things that you owed me, so I did not put them out for anybody yet, but I need to get them done. So if I don't have whatever it is you owe me by tomorrow is going to be the last day for some of it anyway. Some of you are done, and I've started putting yours together, but I really want to get them out. So if there's anything in there that even if you are turning in late and you want partial credit, if it's within the range, like last week's homework, for example. Last week's homework would be due today. If you don't get it by tomorrow, it's a what?
0.
Yeah. You remember how you guys remember how the late policy works?
After a week, it goes away.
Yeah. So you only have that week to get it done. If it's late, you get a little bit of a ding, right? But if it's really late, you get a bigger ding. So reminder, here it is. I have it in here. Oh, I just passed it, but whatever. Oh no, that's not it. Nope, wrong one. It's in the preface at the front of your binder. It's on page like 4 or something, isn't it? Let me see. Let's remind ourselves what it is so that everybody knows. Everybody gives me stuff. Woo. It's right there. It's on page 3. You can't miss it. Right there. If you're absent, make every effort to turn it in digitally, right? Especially if you know you're going to be gone. Get it done. Final project, midterm, and exam are not accepted late, nor are they eligible for partial credit. The only case there is like if you're sick, like 2 years ago, we had to have mom's proctor exams at home because there was COVID and it was a disaster. Your mom, yeah, Ms. Benson proctored exams. It was, yeah, you had the flu or something. Yeah. Class participation. That one you don't get dinged on if you're late. That one you get full credit as long as you do it within 8 days. So if you missed last week, which was the last day of the quarter, and you were absent, you have till tomorrow to watch the video and like it so that you can get full credit. That one you don't get dinged on. You watch it sometime in that 8-day span, you're good. Now what happens with the homework and stuff? A day late, you're going to lose. It says 5 points, but you can think of it like almost like a 5% thing. So really it's a little more than that, but you'll lose something on your homework. And then if it's a week late, 10 points or roughly 10, depends on how many points the assignment actually is. I need to change a little bit. And then 8 days. So look and see. You guys, some of you guys are like really pushing that, and I'm going to make sure people get dinged for good. We good? Okay.
The other way around, glass blocks ultraviolet and lets infrared through.
Ah, there you go.
Okay.
Let's put all the nerds together and let's see what they all say. All right, come get your money and you're good. Shoot.
Okay, this is a lot.
Oh yeah, he's got, yeah, look at all of his stuff. That won't work, this won't work. That one will work, this one will work.
Okay, dude, you can't.
Oh, thank you. Close. Excellent, gang. Stop, end this meeting for Jack and Liam, whoever else. Bye, gang. See you later.